And so we gradually move to new parts of the lecture, and we can also see how successful they were for some problems. And right now, when we are talking about self-supervised metric learning, often art phase or cost phase or something like this is the most desired solution that was kind of related to the solution of winners. But also you can see that there is some approaches that don't use this contrastive paradigm, but instead try to solve this problem as classification. Also, we can try to do this if we don't have supervision, and I want to focus a bit on a different model called MOCO, that kind of similar to what we considered before, but we did not have time in previous lectures to think more about it. At first, I would like to introduce new loss function. In particular, we will consider info and the contrastive loss in this corner here. And we have embedding of an object, embedding of a positive object, and embeddings of negative object, negative case. And so we want to the scalar product qk plus to be big, and the corresponding distance to be small, and vice versa for these embeddings. We want them to be as large as small as possible, because we want them to distance to be as large as possible. Or we can say something about closeness of this approach to softmax. It, in this case, does not make much difference. So we have some this pretty standard loss for contrastive learning when we have this counterpositions for positive object plus, which we define as plus, and negative objects with I indexes. And so we have this loss. And in usual contrastive loss setting, we have a batch of negative objects, and we want them to be different from positive objects. Okay, standard setting. What two new things MOCO, momentum contrast, implement? You can see we have this momentum word here, and we have contrast. For contrast, we see that we have pretty standard approach to define the loss function. For momentum, we say that right now, for creating of embeddings for these negative objects, we use a different encoder, which we called key encoder. It has parameters theta k, and our main encoder, which we will use for inference in the final stage, is theta q. And when we want to have parameters theta k, we modify them with this momentum heuristic. We say we have this m, which is quite close to 1, as you can see. And so we keep all parameters, but update it slightly with parameters of this new query encoder with a coefficient 0.000. One. And so we slightly modify it, it's much more smoother. And also what's more important, it's different from query encoder. So it's in this way, it's this smoother way. We match this initial encoder with its smoother version. And this version is kind of different. It's something similar that we observed when we looked at Bayol, when we have this online model and another model. We compare our embeddings from. And this coefficient is small because we want it to be want to backpropagate through this data too when updating okay, we update only momentum encoder, but we don't want to have big updates here. Also, another comment is that we have another heuristic that helps us to make model better. It's called a queue of objects here. In the initial, statement for contrastive contrastive models, it's quite natural that we have some mini batches of objects, and this mini batch is the same at each step. But we have this fundamental flaw for contrastive learning. We often focus too much on some particular negative object at each step, and this leads to the scenario when we push some positive objects from some negative objects, but this can lead that we push these objects to another negative objects, and this can be the problem. So we want to compare the embedding of positive object and anchor object to as many objects as possible. So I want to have more batches here, and we have a queue of batches. We can schematically draw them like this. So we have this initial batch. During the second sampling step, we have another batch of negative objects, and we keep all of them in our training step, in our denominator here. Then we have the third one, and we also keep it here. So we now have a batch of objects, a batch of negative objects that consists of these 3 mini batches. Then at some moment, we say, okay, we looked enough at these negative objects. So we have this fourth mini batch, and we form the final batch, not from all 4 batches we have, because we have some limitations in terms of memory and so on. And we have it like this. And also, as we have this slightly modifying encoder for as key encoder, we can backpropagate and calculate embeddings and complete embeddings only for this last mini batch, and keep embeddings from previous mini batches as it is. Don't update them, and it's still efficient to try to have some contrast between query encoder of positive object and encodings of negative objects. So in this case, we don't have to recalculate embeddings from previous mini batches, but still can use them. So we have a larger batch size in fact, and this leads to smoother and much more powerful model. So this is the main 2 ideas for this MOCO approach. So we have this momentum for key encoder, and this key encoder is different from query encoder. And also we keep this dictionary of objects. We have dictionary of negative objects to compare to in our contrastive approach. Also, it's interesting to compare this approach, momentum contrast, to, for example, SimCLR. SimCLR reported that MOCO is much worse. And what's the reason why this approach is worse? The obvious reason is that SimCLR provides some superior loss function, and because of this, it works better. But it also can be the case that there is something different inside it. And we consider 3 improvements that were made by SimCLR compared to the first version of MOCO. The first heuristic was to use much larger batches of size 4K objects or 8K objects, or really large batches. And we saw in Bayol paper that it's critical to have large batches for this kind of self-supervised approaches. Also, in SimCLR, we have updated projection head. So in MOCO, it was like 1 full connected layer. In SimCLR, we have 2 layers of MLP, and we have some nonlinearity between them as usual. And this also can be beneficial. And also there was another augmentation provided by SimCLR, I'm sorry, and it was about Gaussian blur augmentation here. And so it makes sense to compare MOCO with these heuristics to SimCLR. And as we can see, if we have batch size of 256 and have this additional head and additional augmentation and also like slightly different learning rate schedule, we can see that Mocha outperforms SimCLR significantly. It's like the gap is about 5% if you have only 200 of epochs. So we can say that Mocha is a winner if we have limited amount of resources here, and if we have limited size of batch. If we increase batch size for SimCLR, we in fact improve the model, and now we have this result, this accuracy for a linear classifier for ImageNet on top of trained embeddings. And we can see that it's pretty much bigger, pretty much closer to Mocha version 2 performance. Also, if we train model for more epochs, we can say that, okay, SimCLR is better, okay, than it was for 200 epochs, but still it's not big enough. It's strange that the afters use different batch size, but maybe they don't have time to train SimCLR for 1000 epochs with these large batches, because it's like multiplication of 2 for training time. And I think it was already large enough here. But what we can see is there's some gap between accuracy for Mocha versus version 2 and SimCLR here. Also, we can try not to compare SimCLR and Mocha with all augmentations, all improvements on, but also try to have some ablation study and see what happens when we do some additions, some improvements of the model step by step. The first improvement, we add this modified projection head. We have significant improvement of quality for our ImageNet accuracy. Okay, then we try this augmentation here. Only augmentation, only Gaussian, only blur augmentation. And we can see there is some improvement compared to initial version. So we can try to turn on both these heuristics simultaneously. And we have additional improvement of the model here. And also, if we apply this cosine learning rate scheduling, we have a very small improvement. And if we train for more epochs, we have additional improvement. So what lessons we can learn from here is that, okay, I hope everyone can find his way to the lecture today. Yeah, no new concerns, and I hope that the record will be available after the lecture. But let's go back to it. And so we can see that we need more epochs. We don't need larger batch size for Mocha, because it is like quite natural for Mocha to keep the mini batch size low and use these previous batches to improve the model. And also we see the importance of projection head and importance of additional augmentations. Right augmentations are still is a key to have a good performance in the end. And as we had some time to talk about about supervised, self-supervised models, we also I want also to put some emphasis on another approach related to self-supervised learning and to the recent SOTA results in parallel twins. And according to the paper published in ICML 2021, it's like the SOTA for self-supervised. And what's the difference here? And what's the same actually? It kind of pretty much the same to what we had before. And what does it mean? It means that we have this augmentation, this view step here to generate two distorted images. Then we have some embeddings after like encoder F, and also a projector. That's like additional necessary step, as we found out during the previous lecture, and scientists found out this too. a bit earlier. So we have some embeddings here, and we have some cross correlations between these two embeddings. We have this correlation between different dimensions of features, and we want these cross correlations to be as close to diagonal matrix as possible. So we kind of try to disentangle embeddings in this projection space. So we want these features not correlate if you have like different version, different version of the same image, different views, different embeddings. Okay, the loss function so is pretty simple. We say that as a diagonal, we want these cross correlations. Okay, this cross correlation has pretty standard formulas. We compare embeddings for for two objects and for two features, two embedding features for these projections of the embeddings of these objects, A feature and J feature, and two views A and B. And we measure cross correlations. And as a diagonal, we want 1. So we have this square loss between 1 and this diagonal cross correlations here. So there's a square of the difference. And also we have some hyperparameters, hyperparameter lambda, that introduces the penalty for cross correlations between different features to be large. So it's CAJ squared. And this is another term that kind of disentangles our embeddings. And so we have this pretty easy loss function. And what we can see here, you can see that performance is pretty similar to BIOL here. So if you consider top 1 ImageNet or top 5 ImageNet accuracy for linear models on top of trained embeddings, we can see that, okay, it's pretty much the same. Also, we have this another top performer, which we don't consider because we don't have time as usual. And if we see another benchmark here on fine-tuning using 1% or 10% of trained examples, we see some improvement over what we already saw for BIOL. We can say that this kind of embeddings, for some reason, provides some improvement over BIOL if we have this semi-supervised learning set. So in this case, we say that barrel twins, maybe because of this disentanglement, works pretty much better compared to what we had in BIOL version. Okay, now I think it's time for you to turn on the cameras and for me to have a screenshot of your happy faces this early in the morning. So let's do it. Okay. Andrei, do you have some problems with camera? Shakir?
Yeah, I have a little issue with the internet.
Okay. One moment, and I will be back to you. Okay, so let's continue with the class. And so we talked a lot about different versions of self-supervised learning. And also some of them are quite recent and quite good in terms of performance. And so the next reasonable question is why it works. Because right now we have, for example, some approaches that don't have negative examples and some approaches that kind of use very strange heuristics. And we can examine them in ablation studies and see, yes, all these heuristics matter. And because of this, we need all of them to work fine. Also, we can try to prove some theorems on the dynamic of loss function. And we can say, okay, let's simplify our model, as we usually do when we want to prove some theorems. And we will try to examine sim-CLR learning and a variant of BIOL when we have no negative examples here. And so we say that we have the same input, we have some augmentations here, and we have some contrastive mode. And it turns out then if we analyze this dynamic for simple networks, so it's not convolutional layer networks, but we have rather threefold connected layers, we can we get the features we have in our data that's produced by our augmentation. So try to, and we can learn we can learn these features related to augmentations, and we have this disentanglement, and so we can say that we do learn something, meaningful when we train this contrasting loss here, and training dynamics leads us to something good in this case. So I wouldn't want to deep dive, but want to consider this from other point of view. Are supervised and self-supervised model different? What we are doing? We train two models. One model self-supervised, another one supervised, and we try to pull the same data set. For supervised model, I suppose we have this common cross-entropy loss, and for self-supervised, we use not cross-entropy loss, but we use this mock-up version 2 model to make training take reasonable time. And what we trying to examine is how fast we escape local optimum. We find the gradient. Okay, we have this loss function, and we move along the gradient here. So we try to go out from, okay, maybe it's not the best figure here. So we say that we try to examine the loss, the optimum of the loss as fast as possible for moving in the direction of the derivative. And we see the dynamic of this loss and how fast we escape. And we escape self-supervised optimum faster. It means that when we try to draw this projection of this optimum for self-supervised and supervised, we say that for supervised, we have wider optimum. So in this case, we say that, okay, we have this different characteristics of optimal, and for self-supervised, it's a bit worse. And we observe the similar behavior when we look at local optima and make not targeted steps, but we make random steps. In the left, we see the name, okay, in the center, there is optima, and we try to make some steps in random directions, and then project this figure using PCA, and this whiter areas correspond to lower loss function, and darker areas correspond to higher values of loss function. And we can see that the figure is very different for self-supervised and self-supervised optimum. And we can say that it's much whiter on the left. It means that in a neighborhood, we have much larger number of optimums related, okay, of better points, and we very quickly escape this optima if we move in random directions from self-supervised optima. So we can say that in this case it's false here. Also, we can try to find out is the path between the initial parameters and the parameters after fine-tuning is different for supervised and self-supervised approach. And we compare this lengths of optimization. So we compare, okay, we have this number of iterations, which what we do, and we try to measure the L2 squared norm here, and like sum all the steps, lengths of all the steps we have during optimization. And we see that for supervised optima, it's shorter. For supervised optimas, like closer to something we have after fine-tuning, or fine-tuning to a particular problem, so we transfer to this FGVC aircraft dataset. Also, when we compare the distances between initial optima and optima we found, we also see that for supervised approach, it's much closer to. And it's kind of, for me, it was a bit surprising because I expect that self-supervised optima have slightly better generalization ability because it wasn't trained for some supervised problem, but instead we see that it's not the case. At least for Mock-over 2, we have still very unstable solutions, very unstable embeddings, and this is not related to self-supervision, but rather to the nature we have for self-supervised models. Okay, and now let's examine some results we observed when we were trying to apply these approaches, and not only we, but other people too, tried to apply these approaches in real life for some problems slightly different from images. In particular, we'll consider sequential data. Okay, it's quite natural for this course to consider sequential data. And the first thing we considered was contrastive predictive coding that you were told during the previous seminar. It's also self-supervised method, and it based not only on contrastive approach. So we try to compare the embeddings obtained at each step and make embeddings obtained at like similar steps to be close and different steps to be far from each other. But also we have this after regression part. We try to predict from the current embedding obtained by applying some LSTM-like model to our encoders of initial data to predict embeddings like this here, 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 and here. And we can try to see how this, this model works, how to train this model. And so this literature and what we observe actually when we use this info and CU loss, which I introduced like this softmax for a pair of positive object and anchor, and many pairs in the denominator related to positive anchor object and negative objects. And we can see that yes, loss decreases, but it's doing it quite slow and in a lot of epochs to go to the region when we have this constant loss or like this oscillating a lot. Also, we can see that it oscillates. We have very large difference between losses for different batches. And this may be due to this particular peculiarity of CPC approach, but also it happens for different loss. As for example, if we look at STB loss, we have the same large amount of noise and very small convergence. Maybe what we can try to do is have more objects in our batch. But right now, when we compare results obtained in our paper to results obtained in the article, also we tried less number of epochs because of GPU constraint. We see that, okay, we have to train a lot more to reach the accuracies of from the article. So you can see, okay, we have this and this and this and this. Okay, the difference is like 0.2, and not because of some architecture changes, but because we should invest more computational resources. And maybe it's kind of sad story about these approaches. We either should do very clever augmentations, very clever approaches, but we need a lot of computational power to make all this work. And we have to take a lot of efforts to consider these types of models. Okay. Another question is, how can we apply this to a particular data? As said, to a particular very specific domain. And as an example of this domain, we consider a sequence of loans. A particular sequence of transactions by a client of Sberbank. The structure of the data is the following. We have this MC code from list of about 1,000 possible MCC codes, and some amounts related to this cost. So how much money a customer spent during this particular transaction. And so we observe a sequence of these transactions. So a customer started from a grocery store, then he or she went to drugstore, then to clothing store, and again to drugstore. And he was too impressed about his spending here at the clothing store. So this was the structure of our data. And so we say, we don't have this natural embeddings. For images, we can have this blur or distortion, but we can try to form different views of the same client, of the same user. In this way, we can say, let's take two subsequences of the whole sequence. So we have the whole sequence of transactions, like 1,000 of transactions, and we form some subsequences of like limited length, 1,000, 2,000, and so on. They can intersect and they can not intersect. We don't care much. But what we care about is when we apply encoder, and we apply our encoder model F here, and obtain embeddings for subsequences. We want the distance between these two embeddings to be small. We want to minimize the distance between these two types of embeddings. Okay, but we can do the same steps for different customers and obtain embeddings for a different customer with the same encoder model. And we have like two embeddings here, and they also should be close to each other. And also in our contrastive loss approach, we want the distance between these embeddings and these embeddings to be as large as possible. So this is quite common intuition behind contrastive approaches to self-supervised learning. As you see, we don't need any supervision. We take some parts of user history to make embeddings from it and to compare them, and we hope that embeddings for a single user should be closer to each other. Okay, and we can adopt this kind of self-supervised learning approach. So we have, okay, suppose we have a positive pair. In this case, we have this y that equals to 0 in our loss function, and we saw this guy we don't care about. We care about this guy. And we have in the basic version just a square of the distance between embeddings in the pair. And this is a positive pair, so we penalize for large distances here. And if we look at negative pair, then we have y that equals to 1. That means that we don't care about this term, but for this term, we want the distance to be as large as possible. So we penalize if this distance is smaller than the margin. If it's smaller than the margin, then we have this positive penalty for it. And we have like this margin here, and this distance that's smaller, and we have this penalty. Here we multiply it by itself, so we have a square of this part of our contrastive loss, and so we have this basic loss. Okay, to make it work better, the authors, Dmitry Babayev and his colleagues from Sber, tried a slightly different approach and considered, I'm sorry, a slightly different distance here. In particular, they introduced another bound for margin, so they don't penalize for the for this area. So they don't care about if we have too small or not too small. So if it's smaller than beta, it's okay. It's still okay. Okay, it's larger than beta, it's still okay to have embeddings here. And this means that we have this maximum of 0 and the distance minus another bound for margin, lower bound in this case, and our upper bound m that we already had in our previous version of loss. So we consider this two loss function, like pretty heuristic one. And so what we can try to say about the training of these different types of embeddings, we start with like the evaluation protocol. The evaluation is similar to what we have. We consider two data sets, prediction of age and prediction of gender on the basis of transactions. We run it sometimes for 5 times, as far as I can remember. And we use light given on top of different types of features. Handcrafted features, malus embeddings. Malus is the name of the approach introduced in this article. Also, we can use both handcrafted features and malus embeddings here and try to input them. And also we can try to compare this to fine tuning and also compare this with alternative, with CPC embeddings, which we discussed like maybe 10 minutes earlier when we say that we have this combination of after regression and contrastive learning approaches. And as we can see, MLS provides better results. And also what is maybe more important is that when we compare handcrafted features and add to these handcrafted features MLS embeddings, we have improvement. And so we say that, okay, it's quite good things, quite good idea, quite a good thing to do. And this improvement is quite significant here. So we have this additional information extracted from the data using embeddings, using models, which is a good sign that we are doing something useful. And also we say that malus is better than CPC here. Here to here, unfortunately, CPC doesn't work well here. We can also try to examine other design choices we have in our data to have ablation studies and, for example, compare a LSTM Garou transformer. As it often happens with non-LP data when we don't have millions of epochs, we have not significant difference actually here, with Garou being the best. So it's interesting to see the Garou beats LSTM, which not often the case for NLP data. But transformers is slightly worse in this particular scenario. Also, when we try to compare different losses, we say that the best approach is this margin loss. We had 2 slides before. And original triplet loss and contrastive loss can be not as good as it. And so be it. And also histogram loss is something you should pay attention to. But also you see that the difference is not big, except for this binomial deviance loss, this initial one. So we can say that otherwise all other approaches work pretty much the same. Also, the authors tried different sampling strategies, which, as we know, is a very important part of how can we deal with self-supervised approach, how can we improve it, or how can we degrade the performance if you're doing it wrong. And if we have this random slices, which means that we just put them random, and we don't care about just joins or joint samples, so we can have some intersections between intervals taken from one customer. We still have some improvement here. Also, we say that if we have different strategies for negative sampling, the best option is hard negative mining. And as you can again remember from previous lecture, it means that we put as much data as possible. Maybe if we will be provide something more clever, we can try to do better using smaller batch sizes, not sampling a lot of batches, a lot of pairs, but try to focus on something. For example, we can try distance weighted sampling, and it's kind of close and requires less computational resources than hard negative mining. So you can see yet most of the steps here are still important. We still need correct sampling strategy, correct model, and correct loss function. But in this case, this is difficult, maybe not that significant. Maybe in my hypothesis is that these two particular data sets are not very large. And for images, we have a different picture because image is much larger than this age and gender data sets. And I suppose I have some statistics a bit later. Yes. So for age, for two types of age data sets, we have about 30,000 of clients, not a big number here. Yeah, a lot of transactions, but it's because we have a lot of transactions, about like 100 for each client, but generally the sample size is not that big. And it's the story is the same for gender. We didn't include it here, but the amount of data available in the gender data set is quite close to what we observe in age data set. Also, maybe the data complexity is a bit smaller because for transactions, we have this limited number of MC codes, and amount is something that's pretty easy to grasp, pretty easy to understand and to encode, and this is not the case for images when we have a lot of pixels and kind of hard to say about the output of the model by a single pixel. It's much easier to say something about the gender of the age from a single port chase, I suppose. So I suppose that maybe some of these parts, some of this conclusions are due to smaller data set and simpler structure of this event sequences data. Also, it's okay, maybe it's a bit side work, but I want also to show you that we tried some other serial attacks on these models to see if this conclusion still happens, still works when we consider bank transactions data and bank transactions models. We consider it like this 4 data sets and different strategies for adversarial attacks. Sampling full is just random sampling and selecting the best according to a surrogate model in like this black/gray box scenario when we train a model using a separate or intersecting but smaller amount of data. We also consider a variant of FGSM in embedding space because we don't have this gradients in our initial space because it's discrete. And so we use FGSM in embedding space, and we somehow try some additional heuristics and some additional changes to make the model work. And what we can see when we change two tokens here, so word error rate, so number of words we changed or deleted or edit, then towards like transactions, we say that accuracy is similar to an accuracy of a random classifier here. So we just break the model completely, and we can do it even better here. And it was also the case for other data sets for client living and for Score, and we still break it a lot. Okay, but also, okay, we can say that this adversarial text exists also in this scenario for the simpler data. And we still can break a model, and so be it. But also I wanted to show you how we can apply similar techniques for oil and gas data. So the problem is the following. We have a data on a set of wells here. And for each well, we have this login data with 4 features available. Here there's some example of time series related to each well, to each drilling. And so we want to produce some embedding. So our representation produces meaningful distances. If we have, okay, I don't have the slide. If we have two similar wells, two wells that has close properties, then we want this distance to be small. If we have two distinct wells with very different properties from different oil fields, we want this distance to be large. So the problem is how can we construct an embedding? And the idea is the following. Okay, we for sure have some processing step. It is a must because we observe a lot of missing data, for example, for our oil and gas drilling data. Also, we say, okay, we should somehow train similarity model, and we don't have labeling. And even if we have labeling, number of training examples is quite small here. So instead, we try to sample intervals. Quite similar to what we did for transactions data. So we have this whole data. So we have this depth of a well, and we select some intervals from this well. And so we can say that if two intervals are close to each other in terms of depth, or they belong to the same well, then their similarity score should be high. And if we have two intervals from two different wells, then this similarity score should be low. So this kind of classic contrastive learning approach, pretty similar to what we observed for this article on metric learning for transactions data. So we just sample intervals from a long interval and believe them to be close or to be far to each other. If you have like positive pair from the same well or negative pair of intervals from different wells. So if we calculate the similarity, we can apply different types of metric or similarity learning in this self-supervised way. And so we have similarity between pairs, and then we aggregate scores. We can do it in two ways, like micro and macro way. For micro way, we say that we have these embeddings for each interval, like this interval, sometimes series here. We have some embeddings. Same story for different interval. Again, embedding. But the dimension is same. So we can put all these embeddings here for a well and have this max or min pooling to get an embedding of the same dimension for the same value. So we took maximum value in this case, this scenario of max pooling at each dimension, or we have like min pooling instead. And maybe sometimes it can work better. This is kind of what we call micro aggregation. If we are talking about macro aggregation, we say that we sample intervals from first wells, from second wells, calculate distances. So we have this embeddings for first distances. Okay, intervals from first embeddings and correspond, or from first value corresponding embeddings, and the same story for the second value. And we calculate distances between x1, g1, or sorry, y1, x1, y2, and so on. So we have this matrix of distances. As we expect that it would be largely only sample part and calculate part of those distances. And then we take some quantile or mean value of the distances we calculate for these pairs to get the distance between wells. And if from distance it's quite easy to get a similarity score. For example, we can have this distance between wells divided by some temperature tau exponential of minus this guy to have some similarity score. The distance calculated in this way and similarity score. What kind of architecture we use? Okay, this is about the sampling strategy, quite something we discussed, and also how we obtain the final result, the embeddings. We do it actually in this way here. We have two intervals. We run RNN over the measurements for each interval, and we have some embeddings. And we have after it full connected part of three layers to have this similarity measure in the end here. And okay, we can try to do a slightly different way, but this approach showed the best results and quite similar to other self-supervised approaches we observed in recent years. We kind of have this initial part, this encoder, to produce embeddings, and then we have this projection head, and after projection head, we compare obtained embeddings, for example, with like cosine distance or Euclidean distance between these two guys here. Euclidean distance was a bit better compared to our initial distance here. Okay, I would not like to focus here, but it's, I suppose, pretty obvious that we again have this triplets, again has this embeddings, and after embeddings to calculate distance in different ways. So how should we validate our approach? At first, we can validate our similarity model. So we say that some intervals are similar, some intervals are dissimilar. And so we have this classifier model for the pairs of intervals. And we can compare logistic regression, gradient boosting on the base of simple features, just time series alone. And also we compare them with different types of RNNs. In this case, we have embeddings produced by this neural net here. And so yeah, we have some common quality metrics. And what we can see for different processing strategies, XGBoost is slightly better, but we have a decent performance for different types of RNNs here. And actually, after we obtain this first result, we now have like a better version of our neural network, and it works very close in terms of performance to gradient boosting. But it is not published yet, so I don't present it here. Also, we tried a different approach to compare of how well we work, how well our self-supervised approaches. And as we focusing on distances, maybe it makes sense to have some clustering based on distances and balance and see how this clustering is different from what we expect. To do this, we hired an expert, and our expert labeled wells and intervals with some labels here, and we have like 10 classes in total. And also we have embeddings of wells or intervals. We can try to cluster them into 10 clusters. And we can try to find correspondence between our clustering, so labels we have for our intervals of wells, and our classes labeled by the expert. And in this case, we don't know the exact correspondence between classes and clusters. So we use some clustering quality metrics. And so we look at the pairs. Here, the simplest way to think about is rand index. It's the number of correct pairs. What is a correct pair after clustering or labeling? We say that we have clusters, these cycles, big cycles, and we have labels like the color and shape of a particular object. And so we can look at some pair. And this is a correct pair because it belongs to one cluster. And also it belongs, okay, all objects from this pair belong to the same class. So it's in one cluster and in one class. If we have similar station, but okay, these two different objects belong to different clusters and to different classes, we also correct. Also, we can have incorrect pairs when we have different classes, but the same cluster for object labels. And if you have different clusters, but the same class here. And so we calculate number of correct pairs and divide by the number of pairs if we have n objects here. So it's n minus 1 plus 1 divided by 2. Here. Oh, that's not. Now it is. So we want this rand index to be as big as possible, to have large number of correct pairs. And we also adjust random index to have it, to normalize it, I would like to say. So we divide from rand index expectation of R index for random perturbation and divided by maximum possible value minus again expected value. So this value now is between -1 and 1. 1 is a perfect match, -1 is a perfect mismatch of clustering and labeling. And we can see that these scores are higher, significantly higher than 0 if we apply clustering on top of what we already have. So it means that our embeddings are useful when we are trying to cluster something. So we can say that this approach, if applied in a correct way and take into account the experience gained in other areas, it's quite good and can lead to reasonable and significant achievements in other areas. And also quite interesting that the same ideas like projection head can work here. And also that we don't need a lot of data for this to start to work. For example, here we have, I suppose, about 200 of wells and about like 4,000 of measurements in each well. And it's okay to start thinking about application of self-supervised approach, maybe because the data is, again, not that complex, but complex enough for self-supervised learning and neural networks to make sense. So a few final words about, okay, also I say something about after regression, but I hope maybe I want to mention one approach named Electra here, and so be it. So we have this basic after regression models for sequential data, like masking language model when we try to predict, like when we have some sequence of tokens here. We drop some token and try to recover it to predict what is here. And this is what's called masked language model. And we can try to approach this in different ways. For example, in GPT-3 style model, we predict the last token here because it's kind of after regression models that are targeted at predicting the next token, the next word. Also, there is another interesting approach that somehow connects self-supervision and adversarial attacks on tokens and sequences on objects in general. In this case, it's called Electra. And the idea is the following. We have this initial sequence here. And we replace one token with some other token. And we don't tell model about it. Because some token is replaced, please find out what token is the most probable to be replaced here. And so we can calculate again some scores, some probabilities related for that this token is replaced. And so we can define a loss function and kind of after regression model, and also somehow related to adversarial words because we find something adversarially or randomly replaced, and we can be quite successful about it. So this is called Electra, and this is maybe one of the most interesting present papers related to after regression models that quite naturally fits into the framework of sequential data models. So a few final words. We see that this is self-supervised approach and in general similarity learning, if you have some supervision works, there is a lot of heuristics to think about, but it works, especially for large data set. It works, and we have meaningful representations that we can reuse for many problems here. And we can try different scenarios. I suppose that fair comparison provides like kind of similar performances, but slightly better performances would be for approaches that are now at the top and published recently, because you can look at tremendous amounts of experiments provided in this paper. So they all show that there is some problem. Also, we don't completely understand what's going on when we are trying to work with self-supervised models. Sometimes we can train model even without negative pairs. Kind of surprising, but it works. Also, we have two general ideas: generative or after regression and contrastive approach are true self-supervised learning. Both of them work, but I suppose that the best one, what is the best, depends on the problem. For if we target after regression downstream problems for application of this embedding, then maybe we should use generative models. If we want something more general, maybe we can have contrastive models. Also, we can say that fine-tuning is another area to explore, and there are some, I think it's underdeveloped, and people don't pay enough attention to how should we do fine-tuning of a particular problem set. What's the right tool to do it? And in general, tricks are important here. We should put a lot of attention to how we do augmentation, what is the batch size, and how many epochs do we have to train our model. And only for careful examination, we can obtain sort of results. What we can try to do slightly worse if we apply this to new areas, but still good, some significant results. For example, we can see this for transactions data and for oil and gas data, but still we need a lot of time memory for these models to succeed. So I suppose that's all for today. Thank you for your attention and have a nice day and a nice section related to your projects if you need it. So goodbye.